I'm Dr. K. Raghu Mohan Reddy, Associate Professor of Mechanical Engineering Department. Course name is Unconventional Machining Process. Today's topic is Abrasive Jet Machining and Material Removal Process. Right. So at the end of this session, student will be able to understand the working of abrasive jet machining process and understand the material removal rate mechanism and its parameters. So these two are the course learning outcomes of the today's topic. Right. Okay, before we going to discuss the history or the prerequisite pre-information of this topic, first let us come to non-traditional machining process. Under that we have three categories. One is mechanical, thermal, chemical and electrochemical. So under mechanical, already we have discussed ultrasonic machining. Now we are going to discuss abrasive jet machining and water jet machining. However, in this topic, let us confine to abrasive jet machining. Right. This is the schematic diagram of abrasive jet machining. Okay. See, first gas supply, filter, pressure gauge, regulator, mixing chamber, over that hopper, vibratory source, nozzle, jet. This is the workpiece where we have to work for the material removal. So this is the abrasive jet machining schematic diagram. Now let us see the various components discussion in the next slide. Okay, as part of introduction, abrasive jet machining is a material removal process that utilizes a high velocity stream of abrasive particles suspended in a gas, usually air or nitrogen, to erode material from the workpiece surface. It is a non-traditional machining process suitable for machining brittle materials such as glass, ceramics and composites, as well as hard and heat resistant materials like metals. So this is the introduction part of this abrasive jet machining. Right. The basic components of an abrasive jet machining system include abrasive delivery system. That is the first one. Abrasive delivery system. This system consists of an abrasive hopper, this one, where abrasive particles are stored, and feeder mechanism that controls the flow of abrasives into the mixing chamber. Okay, right. So abrasive delivery system consists of an abrasive hopper where abrasive particles are stored and a feeder mechanism that controls the flow of abrasives into the mixing chamber. This is the mixing chamber where the mixing will happen. Right. Next, gas delivery system. It provides the necessary pressure and flow rate of gas, usually air or nitrogen, to propel the abrasive particles towards the workpiece. Okay, so this is the gas delivery system. Okay, right. It provides the necessary pressure and flow rate. Okay, so here pressure gauge is to control the pressure, and the regulator regulates the flow of gas. Okay, right. Mixing chamber. This is where the abrasive particles are mixed with the gas stream to form the abrasive jet. So in this mixing chamber, the mixing will happen. Okay, abrasive particles are mixed with the gas stream. So abrasive particles will come from the hopper, where the gas stream will be supplied through this gas supply unit. Right. Next, nozzle. The nozzle directs the abrasive jet onto the workpiece surface. Okay. Nozzle can vary in shape and size depending on the application requirements. Okay. Right. Next, workpiece holding system. So here the workpiece will have to keep the workpiece without disturbing while the jet strike the workpiece. The workpiece is securely held in place to ensure accurate machining. Right. Workpiece holding system. The workpiece is securely held in place to ensure accurate machining. Okay, right. Right, the process of abrasive jet machining involves the following steps. First one, abrasive mixing. Second one, acceleration. Third one, impact. Fourth one, controlling parameters. So from this figure 2, we can understand the process of abrasive jet machining. First one, abrasive mixing. Abrasive particles are mixed with the gas stream in the mixing chamber. Right. Abrasive mixing. Abrasive particles are mixed with the gas stream in the mixing chamber. Next, acceleration. The gas stream accelerates the abrasive particles to high velocities. Okay. So, acceleration is required to enhance the velocity of these particles. The high velocity abrasive particles impact the workpiece surface, causing material removal through erosion. Okay. Here, due to impact of abrasive particles, the workpiece surface causing material removal through erosion. Next, last one, controlling parameters. Various parameters such as abrasive type, particle size, gas pressure, nozzle design, standoff distance, and a traverse speed are controlled to achieve the desired machining results. Right. Abrasive grades. In abrasive jet machining, in simple it is called AJM. A focused stream of abrasive grains of Al2O3 aluminum oxide or silicon carbide carried by high pressure gas or air at a high velocity is made to impinge on the work surface through the nozzle of 0.3 to 0.5 mm diameter. This is very much important. So here nozzle diameter is very smaller, 0.3 to 0.5 millimeters. And abrasive grains are Al2O3 or silicon carbide. Right. The process differs from sandblasting in that AJM has smaller diameter abrasives and a more finely controlled delivery system. The workpiece material is removed by the mechanical abrasion action of the high velocity abrasive particles. AJM machining is best suited for machining holes in a super hard materials. Okay, right. This is about abrasive grains. Right, machining system parameters. In the machining system parameters shown in figure 2, so this is figure 2, a gas, nitrogen, carbon dioxide or air is supplied under a pressure of 2 to 8 kg per centimeter square. Oxygen should not be used because it causes a violent chemical reaction with workpiece chips or abrasives. Okay, so usually we have to take nitrogen, carbon dioxide or air. Okay, right. After filtration and regulation, the gas is passed through mixing chamber. Okay, so from this it will enter into mixing chamber that contains abrasive particles and vibrates at 50 H. Okay, from the mixing chamber, the gas along with the entrained abrasive particles with size of 10 to 40 microns passes through a 0.45 mm diameter tungsten carbide nozzle at a speed of 150 to 300 meters per second. Okay, right. Okay, however, this is figure 2. Right, machining system parameters. So in machining system parameters continuation, the abrasive powder feed rate is controlled by the amplitude of vibrations in the mixing chamber. The nozzle standoff distance is 0.81 mm. This is the nozzle standoff distance. That is 0.81 mm. Okay. Next, material removal rate. Figure 3. Let us see the various parameters involved in this material removal rate mechanism. See, air and abrasive stream will enter. This is sapphire nozzle. This is jet diameter. This is standoff distance. That means distance between tip of the nozzle to the workpiece surface. And jet velocity. This is workpiece. Okay, formula and parameters of material removal rate. Right. Here K is the constant. N is the number of abrasive particles impact per unit area. dA, mean diameter of abrasive particles in microns. Rho A, density of abrasive particles kg per cubic millimeters. HW, hardness number of the work material. V, speed of the abrasive particles in meters per second. Okay, right. This is about formula and parameters. Next, material removal rate parameters and influence. The material removal rate, cut accuracy, surface roughness, and nozzle wear are influenced by the size and distance of the nozzle, composition and strength of the abrasives, size and shape of the abrasives, flow rate and composition, pressure and velocity of the carrier gas. Okay, here the material removal rate, cut accuracy, surface roughness, and nozzle wear are influenced by the size and distance of the nozzle, composition, strength, size, and shape of abrasives, flow rate, and composition, pressure, and velocity of the carrier gas. Right. The material removal rate is mainly dependent on the flow rate and size of abrasives. Okay, so here mainly depends on flow rate and size of abrasives. Larger grain sizes produce greater removal rates. So here the grain size is larger, then the material removal rate will be also higher. Okay, here the grain size is larger, then the material removal rate will also be higher. Right. At a particular pressure, the volumetric removal rate increases with the abrasive flow rate up to an optimum value and then decreases with any further increase in flow rate. So, regarding flow rate, what will happen? The volumetric removal rate will increase with the abrasive flow rate up to an optimum value. Okay, up to here it will increase gradually. So, after it reaches that point, then it decreases. So, it has a parabolic curve. Okay, right. This is due to the fact that the mass flow rate of the gas decreases with an increase in the abrasive flow rate, and hence the mixing ratio increases, causing a decrease in the removal rate because of the decreasing energy available for material removal. Okay, at a particular pressure, the volumetric removal rate increases with the abrasive flow rate up to an optimum value and then decreases with the any further increase in flow rate. This is due to the fact that the mass flow rate of the gas decreases with an increase in the abrasive flow rate. Hence, the mixing ratio increases, causing a decrease in the removal rate because of the decreasing energy available for material removal. Okay, right. Advantages of abrasive jet machining include capability to machine intricate shape and thin sections, minimal heat generation, making it suitable for heat sensitive materials, minimal tool wear since abrasives rather than a solid tool are used for material removal. Environmentally friendly as it doesn't involve the use of cutting fluids. Here, no cutting fluids involved. Okay, so these are the advantages of abrasive jet machining. Okay, material removal rate for different materials. For different materials, different material removal rates are occurring. The typical material removal rate is 16.4 mm³ per minute when cutting glass. Okay, cutting rates for metal vary from 1.6 to 4.1 mm³ per minute. Right. For harder ceramics, cutting rates are about 50% higher than those for glass. Okay. For harder ceramics, the cutting rates are about 50% higher than those for glass. The minimum width of cut can be 0.13 mm. Tolerances are typically plus or minus 0.13 mm with plus or minus 0.05 mm possible using good fixation and motion control. Okay. Regarding surface roughness, the produced surface has a random or matty texture. The produced surface has a random or matty texture. Surface roughness of 0.2 to 1.5 microns using 10 to 50 microns particles respectively can be attained. Taper is present in deep cuts. High nozzle pressures result in a greater removal rate, but the nozzle life is decreased. Okay, high nozzle pressures result in a greater removal rate, but the nozzle life is decreased. Summary of AJM process characteristics. Okay, let us summarize. When you take abrasives, when the type is Al2O3 or silicon carbide, size around 25 microns, flow rate 3 to 20 grams per minute. When we come to medium, type of medium, air or carbon dioxide, velocity 150 to 300 meters per second, pressure 2 to 8 kg per centimeter square, flow rate 28 per minute, liters per minute. Next, when you come to nozzle, material of the nozzle, tungsten carbide or sapphire. Okay, tungsten carbide or sapphire. Shape circular with 0.3 to 0.5 mm diameter. Rectangular 0.08 into 0.51 and 6.61 into 0.51 mm. Okay, right. Tip distance 0.25 to 50 mm. Based on the application, we have to vary the tip distance. Next, life. Tungsten carbide 12 to 30 hours of working time. For sapphire, it is up to 300 hours. Next, operating angle. Vertical to 60 degrees of vertical. Area 0.05 to 0.2 mm. Okay, right. Summary of AGM process characteristics. Last stage. It is very much important regarding tolerance. We have to look at it. Plus or minus 0.05 mm. Very close tolerances are agreed. Regarding surface roughness, 0.15 to 0.2 microns. There the particle size is 10 microns. And surface roughness 0.4 to 0.8 microns is required. 25 microns particle sizes we have to choose. Okay. Right. When 1 to 1.5 microns surface roughness, 20 microns particle size, again we have to choose. Okay. Right. These are the references. However, before going to close this one, let us summarize the main content. Okay. Right. These are the basic components. Abrasive delivery system. Okay. This system consists of an abrasive hopper, this one, where abrasive particles are stored, and feeder mechanism that controls the flow of abrasives in the mixing chamber. This is the mixing chamber. Okay. Right. Next, gas delivery system. Okay. This is gas delivery system. Okay, here the gas will supply usually carbon dioxide or nitrogen, and here the filter filters the unwanted gas particles, and here the pressure gauge displays the pressure of the gas. Okay, and the regulator will control the flow of gas. Okay, as per the requirement. So in this mixing chamber, the abrasive particles from this hopper, okay, and the gas from this gas supply or gas delivery system will mix, and we will get the mixing of this gas and abrasive particles. Here in the mixing chamber, abrasive particles are mixed with the gas stream to form that abrasive jet. Okay, what we have discussed just. Okay, here abrasive particles will come, here the gas flow will come, and that mixing of that abrasive particles and gas again will flow to this exit system, and that will come to nozzle and strike the workpiece. Right. Nozzle. The nozzle directs the abrasive jet onto the workpiece surface. Okay. So here the nozzle will play the predominant role. Okay. So here the nozzle diameter and the distance between nozzle tip and workpiece are very much important. Right. Nozzles can vary in shape and size depending on the application requirements. Okay, so this is what we have discussed now. Next, while it is striking with high velocity, the workpiece must be fixed securely. Okay, the workpiece holding system will take care of that one. The workpiece is securely held in place to ensure accurate machining. the workpiece should not deviate from its position. Next, the process of abrasive jet machining is in 4 different setups. One is abrasive mixing, second one is acceleration, third one is impact, fourth one is controlling parameters. Okay, so first one is abrasive mixing. So from this figure, a hopper will be placed on this mixing chamber. Okay, so where the abrasive particles are stored. Abrasive particles are stored. Okay, right. Abrasive particles are mixed with gas stream in the mixing chamber. Now, second one is acceleration. The gas stream accelerates the abrasive particles to high velocities. Okay, here the velocity will be increased. Next, impact. The high velocity abrasive particles impact the work surface, causing material removal through erosion. Fourth one, controlling parameters. Various parameters such as abrasive type, particle size, gas pressure, nozzle design, standoff distance, and traverse speed are controlled to achieve the desired machining results. Okay. All these we have discussed regarding abrasive grains. Okay, what are the different materials of abrasives and their sizes. Okay, and the other machining system parameters, gas, okay, pressures, okay, vibration units, speed, and machining system parameters. That means nozzle standoff distance. Okay, and these are the complete material removal rate parameters. This is the formula already we have discussed. Okay, these are the various parameters influence the material removal rate. Okay, so larger grain size produces greater removal rate. This is very much important. Okay, and here this point is very much important. Okay, at a particular pressure, the volumetric removal rate increases with the abrasive flow rate up to an optimum value. After that, it will decrease. Means, so improve up to this point. Again, after that, it will decrease. Okay, improve, decrease. Okay, right. These are the advantages, and these are the different materials. Material removal rate for different materials. Okay, regarding surface roughness. And this is the summary of AGM process characteristics. Okay, right. So these are the references. Right. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.